Savidi, and this is Lab 3 for Physics 2212. So for some key concepts, first we have the loop rule, which says that the potential difference for a closed loop path is always 0. Then we have the node rule, which says that the current entering a junction is equal to the current leaving the junction, which demonstrates conservation of charge. Then we have electrical resistance, which is that resistance equals voltage divided by current, or V equals IR. And then for capacitance, we said that this describes how much charge can be stored in a capacitor, which we'll see in this lab, which is proportional to the area of the disks and their separation. So the purpose of this lab was to predict the behavior of circuits containing resistors in series and parallel, to use multimeters to measure the actual values of conventional current and potential differences in the circuit, and to examine the behavior of ohmic resistors and capacitors. And then here were the main results from our lab. So for the experiment, we assume that the wire resistance is negligible, and we have ideal voltmeters and ammeters, and the system is our circuit and our surroundings is everything else. So for part 1, we have 2 ammeters in series, and the R total is just R1 plus R2 because it's in series, and then the current is 441 amps. Okay, so for part 2, we reverse the ammeters, and we see that nothing happens. The current stays the same. For part 3, we replace one of the ammeters with a voltmeter, and the ammeter reads 0 amps because the voltmeter has a very high resistance, so it will make it negligible. And then we see that the voltmeter continues to read -3 volts because there is not a voltage drop. So for the voltage drop across the circuit, we used Ohm's law and the loop rule to calculate it. So we see that the current remains constant at 0.02 amps. And then for the voltage drops across the components, we saw a 3 volt increase across the battery, and then a 0.96 volt decrease across R1 and a 2.4 volt decrease across R2. Then for when we put a ammeter parallel to one of our resistors, we see that the total resistance of the circuit is now only 47 ohms instead of 147 from before, because the ammeter has low resistance, so the electrons will flow through the ammeter instead of the resistor, which will lower the overall resistance of the circuit. So for the total current of each resistor, we saw for the 47 ohm resistor, we got 48 ohms, and for the 100 ohm resistor, we got 102 ohms. And then for the resistance of the wire and the ammeter, it should be 0 because it's negligible compared to the resistors. And then for our RC circuits, we measured the time it takes to charge and discharge a capacitor with a 10 ohm and 20 ohm light bulb. And we got that for the 10 ohm light bulb, it took 9.3 seconds to charge and around the same time to discharge. And for the 20 ohm light bulb, it took 18.4 seconds to charge and around the same time to discharge, as they should be relatively equal. And then on the left, we see the discharging the charging, and then on the right, we see the discharging. And then for the RC value, we basically plotted these equations on the graph so that it would be 1 over our slope would equal the RC value. And this is just the graph showing that, and we got 3.603 for our RC value. And these equations were both derived from the loop rule. So some sources of error are that this is a virtual circuit lab, so it's an ideal scenario, which does not account for factors that would affect experimental results in real life, and also when tracking the capacitor discharge, there could have been a slight delay in stopping the time. So what if we used a real ammeter? So real ammeters have the same resistance, which would have some resistance which would decrease the total current in the circuit, and then also What if we used an actual battery and no resistor? So real batteries have some internal resistance, so the capacitor would not start charging instantly as it does in the simulation. Thank you.